Let's continue examining the variables in our dataset. We can call header strings again and see what the second column is called. The output reads loan status, so let's examine it more closely. Just like with issue date, we'll begin by displaying the entire column with the help of indexing. We see an array of text values, which all read current. However, it doesn't make much sense to keep hold of this column if all its values are identical. So, let's call NP_unique to see if that's the case. Apparently not, as each loan has one of the displayed statuses. This means there are a total of 9 different possible values for individual elements of this column, one of which denotes missing data. In this case, all of them were displayed on the screen, so it was clear to see there are 9 possible values. But if that weren't the case, we could call the size attribute of the array to get the number of unique elements in the column. Here, we can use the where function to assign a different number to each one. However, we've been told that regressions that determine the probability of default only care if the candidate is in a stable financial condition. Therefore, loan status should be a simple dummy indicator of whether the applicant is in a good or bad economic state. So, we need to split all possible values into either group. Evidently, accounts that have been fully paid have not defaulted, so they are good. Same applies to current, issued, or accounts in grace period. On the other hand, accounts that have been charged off have defaulted. Therefore, they are treated as bad. Same goes for accounts with status default. Additionally, we prefer to be risk-averse, so if no data is provided for the status, we'll treat it as a bad sign. Right. We already categorized 7 of the 9 possible outcomes as either good or bad. But what about the remaining 2? The 2 are being late from half a month up to a month, or being late between 1 and 3 months. Generally, if an applicant is less than a month behind in their payments, it could indicate that they pay whenever they get their salary. But if the latency is greater than a month, it usually means the candidate will probably default at some point in the future because they can't keep up. So we'll treat short period latency as a good indicator and prolonged latency as a bad one. Okay, so we've settled on a good-bad split, but what numeric values should we assign to each one? Well, in real life, we associate positive values with a positive feeling. So we prefer a positive coefficient to signify a better state, that is, a better quality of the account. That's why we'll use 1 to represent good or non-default accounts and 0 for bad or defaulted accounts. Technically, this translates into assigning 0 to all accounts we indicated as equivalent to default, and 1 to all the rest. Like the issue date column, we can write a loop calling NP_where for each of the 9 different outcomes. However, we can be much more efficient and create an array that stores all the bad status options. We'll name it something intuitive, like status bad, and include in it empty spaces, charged off, default, as well as late between 31 and 120 days. It's important to write these values exactly like they appear in the unique array from 2 cells ago. Otherwise, the where function won't properly assign values to all the bad outcomes. Then, in a new cell, we can combine the NP_where and NP_isIn functions to check if the loan status for a given row is included in status bad. If so, assign it a 0, and if not, a 1. To check if this substitution has been successful, we once more call the unique function. The output only includes a 0 and a 1, so we've transformed loan status into a dummy variable. Great job so far. Now, on to the next column. As we display the header again, we see this is the term column. Its contents read as one value over and over, much like the loan status. So we'll once again look for the unique values. If we call the NP_unique function, we obtain an empty space, 36 months, and then 60 months. Hence, we can strip empty space months, which doesn't bring additional insight, and then properly fill out any missing values. We can remove the empty space months part from the back of each string. To do so, We'll call the strip function and save the output over the term column. When we display the new term column, we see only numbers between quotation marks. It is unclear what this term is measured in, so we should rename the column. To do so, simply set the appropriate element of header strings equal to term months. If we look at the header strings output from the beginning of the video, we'll see that terms is the third column, which is the one with index 2. All right. Now that the name is more descriptive, with the help of the where function, we'll assign 60 to each empty space. We choose precisely that value because, as we said earlier, when we have missing data in credit risk modeling, we assume the worst. In other words, 60 months, which equals 5 years, is a long period in itself, representing a loan that is difficult to pay off. Moreover, according to our dataset, 60 months is a worse scenario than 36 months. So we can assume 60 months is the worst term we can potentially end up with in our example. To put it differently, we'll use 60 in this column to represent the worst. After we're done, we can call the unique function to check the contents of the term array. As expected, we get only 36 and 60, so we can move ahead. To conclude, it's a bit unusual when we only have 2 possible numerical outcomes for a given column. This immediately rings a bell that we could just use 1 and 0 instead. If such a situation happens at your work, you can ask whoever scraped or compiled the initial dataset to elaborate why they believe this is the better alternative. In our example, imagine that there's no one to ask. So we will assume that there is a significance to these values, and as a consequence, we won't change them. Moving forward, we'll examine the grade and subgrade variables in our data. See you shortly, and thanks for watching.